All right, let's look at this problem. 3 moles of an ideal monatomic gas go through the 3 processes in the PV diagram below. Knowing that the pressure at A is 4 pascals, the volume at A is 5 times 10 to the third cubic meters, the volume at C is 60 times 10 to the third cubic meters, and the fact that process CA is adiabatic, find the pressures, temperatures, and volumes at states A, B, and C, and find Q, delta U, and W for all 3 processes. All right, so here I have the diagram, and in order to organize myself, because there's lots of different things that we're looking for, I have these 2 tables, and I will have to start filling out things into these tables. Now, I will write my knowns and unknowns in here as well, so let's start doing that. I know the pressure at A is 4 pascals. I know that the volume at A is 5,000, so 5 times 10 to the third cubic meters. I know that the volume at C is 60 times 10 to the third cubic meters. I know that process CA is adiabatic, and then I'm looking for all the other things. Now, some other things that I know, but they don't fit in the table, is that there are 3 moles. So I know that N is 3 moles, and we're dealing with an ideal monatomic gas, so CV is 3 halves R, and CP is 5 halves R. I'm trying to squeeze this here and it doesn't fit. All right, so let's start out by looking at the types of things we know. We know that at each of these states, there should be a set of pressure, temperature, and volume. And if I look at my table here, I see that I have 2 of these things. I have pressure and volume. I know N, so I can use the ideal gas law. So I have PA VA is nRTA. And from here, I can solve for the temperature at A. So that's PA VA divided by nR. Pressure at A is 4 pascals. Volume is 5 times 10 to the third pascals. N is 3 moles. R is 8.314. And when we plug in these numbers, we end up with 802 Kelvin. So I'm going to put 802 Kelvin in here. Now, I know that process AB is an isochoric process, and that means that the volume at A and the volume at B are the same. So I can put that in here. So volume at A and volume at B, so that is 5 times 10 to the third cubic meters. Then I also know that pressure at B is equal to pressure at C. So I will only have to solve for one of them and plug it in. So which one do I solve for? Well, I mean, which process do I go along? If I try to go between this point and that point, I know pressure and volume at A, I know volume at C, so I can use the adiabatic process here to figure out what the pressure is at point C. So for an adiabatic process, so if I go from C to A, I know that PC VC to the gammath power equals PA VA to the gammath power. What is gamma? Gamma is CP over CV. CP is 5 halves R. CV is 3 halves R. So that means that gamma is going to be 5/3. So then here I'm solving for pressure at C, and that's going to be volume A divided by volume C to the gammath power times pressure at A. So volume at A is 5 times 10 to the third. Volume at C is 60 times 10 to the third. And pressure at A is 4 pascals. So that means that pressure at C is going to be 6.36 times 10 to the negative 2 pascals. So we know that pressure. And I'm going to put it at point C. So that's 6.36 times 10 to the negative 2. But since process BC is isobaric, that means that the pressure at B is also that. So that's 6.36 times 10 to the negative 2. Now I can use the ideal gas law for and state B and C to solve for the temperature. So I will do just that. I know that pressure B, volume B, equals nRTB. So that means that temperature at B is going to be pressure at B, volume at B, divided by nR. So pressure at B is 6.36 times 10 to the negative 2 pascals. Volume at B is 5,000, so 5 times 10 to the third cubic meters. N is 3 moles, and R is 8.314. So when I plug in these numbers, I end up with a temperature of 12.75 Kelvin. So I'm going to put that here, 12.75. Now I can do the same thing at point C. So pressure at C, volume at C is nRTC. So TC is pressure C, volume C divided by nR. Pressure at C is 6.36 times 10 to the negative 2. Volume at C is 60 times 10 to the third divided by 3 moles times 8.314. When I plug in these numbers, I end up with 153 Kelvin. So let's put that in here, 153 Kelvin. And we're done with the first table. Now we have to do the second table. Let's see what we know about it already. So we know that process AB is isochoric. We know that in an isochoric process, work is 0 because it would be the area under the curve, and there is no area under the curve. So I know that for process AB, work is 0. Then for process CA, I know that it's adiabatic, and I know that an adiabatic process has 0 heat transfer. So then I put a 0 for the heat in process CA. So I know these things already, and now I'm going to have to start solving for the rest. So let's start with the very first one. From A to B, I'm looking for delta U, and I know that the equation for delta U is the same for all the different processes, and that is NCV delta T. So the delta T will be TB minus TA. So that is 3, CV is 3 halves R, TB is 12.75 minus 802. So change in internal energy from A to B is negative 2.95 times 10 to the 4th joules. So I'm going to put that in here, negative 2.95 times 10 to the 4th. All right, so since I know by the first law of thermodynamics that, I'll just write it, I guess here, Q equals delta U plus W, that means that heat from A to B is also negative 2.95 times 10 to the 4th joules. Now, for process BC, again, the change in internal energy delta U is NCV T final minus T initial. So going from B to C, temperature final is Tc, temperature initial is Tb. So that is 3 times 3 halves R. Tc was 153 Kelvin. Tb is 12.75 Kelvin. So when I plug in these numbers, I end up with 5.25 times 10 to the third joules. So I put that in my table, 5.25 times 10 to the third. Now, work is area under the curve, so that is pressure at B or C times delta V, and that would be Vc minus Vb. So pressure at B is 6.36 times 10 to the negative 2 pascals. Vc is 60 times 10 to the third, and Vb is 5 times 10 to the third. So multiplying these together, we end up with 3.5 times 10 to the third joules. So put that in here, 3.5 times 10 to the third joules. Now for an isobaric process, we know that Q is NCP delta T. So that is 3 times 5 halves R times T final, that's temperature at C, and that's 153 Kelvin minus 12.75. So when I plug in the numbers, I end up with 8.75 times 10 to the third joules. So here I have 8.75 times 10 to the third. Now, I could have used the first law of thermodynamics to solve for this. So Q is also delta U plus W. And I'm just doing this to check that my calculations are correct. So delta U was 5.25 times 10 to the third, and W was 3.5 times 10 to the third. So when I add those together, I end up with 8.75 times 10 to the third joules, and that's the same value that I obtained by using this equation. So these two values are the same, so I'm happy. It means that I've done something right. Now, from process C to A, for change in internal energy, so delta U is NCV delta T. So delta T is temperature at A minus temperature at C. So that's 3 times 3 halves R. Temperature at A is 802 Kelvin. Temperature at C is 153. So that means that delta U will be 2.43 times 10 to the fourth joules. So 2.43 times 10 to the fourth. And knowing that the heat is 0, I have to have change in internal energy plus work being equal to 0, which just means that the work is the negative of this value. So that would be negative 2.43 times 10 to the fourth joules. Now one more check that I can do. I know that for an entire cycle, the change in internal energy has to be 0, because we're basically going from UA to UB to UC back to UA. So UA minus UA has to be 0. So if I add UAB plus UBC plus UCA, then I do indeed get 0. So that means that my calculations are most likely correct.